institutions. Unprecedented, but hugely relevant in an age of globalization and a new set of 21st century challenges that require mass collaboration. The blockchain is a complex technological, economic, and social phenomenon. It calls into question what might have seemed to be established parameters of the modern world like currency, economics, trust, value, and exchange. To make sense of this, one needs to understand it in a holistic context all the way from its technicalities to its aspirational potential. This course is designed to do exactly that, by giving a 360-degree overview to the different dimensions of the technology, its potential application within various industries, and its far-reaching implications for society and economy. In the first section of the course, we give an overview to the blockchain both on a technical and non-technical level. We also discuss the importance of the blockchain within the context of the emerging next-generation internet. In the second section, we talk about the blockchain as a so-called trust machine and how it enables transparency and collaboration. We will look at distributed ledger technology, talking about smart contracts, Ethereum, and decentralized applications. In the third section, we introduce you to the workings of token economies, illustrating how the blockchain and distributed ledgers can work to build vibrant ecosystems through the use of tokens to incentivize behavior. In the last section of the course, we will be looking at specific applications of the blockchain to economy, society, technology, and environment, looking at both existing practical applications and potential future applications. The blockchain is a so-called emerging technology that is currently experiencing very rapid evolution. Within the space of just 2 or 3 years, it has already gone through changes in its technical implementation and our understanding of what it is and can be. As such, our aim is to future-proof this course by not dwelling excessively on existing technical implementations, but presenting a more conceptual understanding of the blockchain within the broader process of change of the emerging next-generation internet. The blockchain is much more than a technology. It is also a culture and community that is passionate about creating a more equitable world through decentralization. It is a movement to disrupt the disruptors, to redesign the internet, and in so doing, shake up existing centralized incumbents. Throughout the course, we will introduce you to this culture and its aspirations. This course is non-technical in nature. It is an introductory course, and thus all terms will be explained. It should be accessible to anyone with a basic understanding of web technologies and economics.
In this video, we're going to give a high-level overview looking at the primary dimensions of this technology that we call the blockchain. We'll first talk about the underlying technology, then the distributed ledgers that this technology supports, then the token economies that can be built on top of that ledger system. We'll only touch upon these topics here to get an overview before going into them in more detail in future videos. On its most basic level, the blockchain is a new class of information technology that combines cryptography with distributed computing, both of which have existed for a number of decades. It was the genius of Satoshi Nakamoto to combine them in new ways, to create a model where a network of computers collaborate towards maintaining a shared and secure database. As such, we can say the blockchain as a technology is simply a distributed, secure database. This database consists of a string of blocks, each one a record of data that has been encrypted and given a unique identifier called a hash. Mining computers on the network validate transactions, add them to the block they're building, and then broadcast the completed block to other nodes so that all have a copy of the database. Because there is no centralized component to verify the alterations to the database, the blockchain depends upon a distributed consensus algorithm. In order to make an entry onto the blockchain database, all the computers have to agree about its state, so that no one computer can make an alteration without the consensus of others. Once completed, a block goes into the blockchain as a permanent record. Each time a block gets completed, a new one is generated. There is a countless number of such blocks in the blockchain, all connected to each other, like links in a chain, in proper, linear, chronological order. The blockchain was designed so that transactions are immutable, meaning they cannot be deleted. Each block contains a hash value that is dependent upon the hash of the previous block. So they're all linked together, meaning if one is changed, then all the other blocks linked to it going forwards will be altered. This works to make the data entered tamper-proof. What we've described here is the workings of the first generation of blockchains, which function largely simply as databases. But the technology is currently evolving to become much more than this, as the second generation already provides the capacity to execute any computer code on the blockchain. The system is evolving to become a globally distributed cloud computing infrastructure, and as we'll discuss in a future video, it remains very much a work in progress when seen from this perspective. Blockchain technology works to create a permanent and secure database. This makes blockchains suitable for the storage of a record or transaction that involves value or in some way needs to be a secure and trusted source of information. These secure, distributed records are called distributed ledgers. A distributed ledger is a consensus of replicated, shared, and synchronized digital data geographically dispersed across multiple sites, countries, or institutions without centralized administration or centralized data storage, being maintained instead by a distributed network of computers. Such ledgers can be used for any form of asset registry, such as inventory or monetary transactions. This might include the recording of hard assets, such as physical property, cars, homes, etc., or intangible assets such as currencies, patents, votes, identity, healthcare data, or any other form of valuable information. This distributed ledger technology enables us to replace a multiplicity of private databases within each organization with one shared database that is trusted and accessible by all parties involved. In this respect, the blockchain enables trust between parties that may otherwise not trust each other. The results greatly strengthen our capacity for collaboration between organizations or between individuals peer-to-peer, without dependency on third-party centralized institutions. Likewise, they result in transparency and many other efficiencies. This is of major significance, as we currently have many centralized organizations that may be internally optimized, but the inter-organizational space in between them is really inefficient, with huge amounts of border friction, redundancy, arbitrage, and resources wasted on competition. By enabling trusted inter-organizational networks, these ledgers enable the formation of organization and collaboration where previously there was none, such as across whole supply chains, or for different healthcare providers to collaborate around the patient's needs, or for different transport providers to collaborate in delivering an integrated logistics network. Likewise, second-generation blockchains offer the possibility to automate the workings of these networks through what we call smart contracts. Smart contracts are computer code that is stored inside a blockchain, which encode contractual agreements. These smart contracts are self-executing contracts, with the terms of the agreement or operation directly written into lines of code which are stored and executed on the blockchain. Like normal computer programs, these containers hold algorithms that take an input of data and, depending on the value of the input, trigger certain events. For example, this might be a financial contract that takes as the input the amount of money in a person's account. If it is above a certain level, then it increases the interest rate that they earn on their deposit. Such smart contracts can be used for automating many basic operations on the network, once again working to remove the need for intermediary third-party institutions, as smart contracts can be trusted, are tamper-proof and execute automatically. Much of the current discussion surrounding blockchain remains at the level of technology and the possibilities of distributed ledgers, as a shared, trusted database enabling the collaboration between organizations, with the resulting disintermediation of centralized institutions and market exchanges. However, its implications go far beyond this, as the blockchain concept is more than just a database or ledger. It is a new organizing paradigm for the discovery, validation, and transfer of all discrete units of value and the development of distributed organizations via token market systems. A token is a quantified unit of value that is recorded on the blockchain. This value may be of any kind. It may be likes on social media, it might be a currency, it might be the integrity of an ecosystem, or it might be an electrical unit. Token networks consist of a network of independent nodes that act autonomously, but through incentive structures and the signaling system of the market, self-organized to create emergent coordination and thus a distributed management system. For example, we might create a clean air token, where anyone who provides a service that contributes to the maintenance and provision of clean air can earn tokens, for example by planting a tree, while those who pollute by, say, operating a combustion engine have to pay in their tokens. Thus, instead of having a centralized authority and a Clean Air Act, we have a token market that works to create signals that align people's incentives with maintaining and growing the underlying resource. Likewise, this same model could be applied to the management of technology infrastructure. As an example, we could think of traffic control. We currently have traffic control systems in cities whose operations are monitored by centralized control centers. But in a world of autonomous vehicles and the blockchain, cars could signal to each other, peer-to-peer, bidding tokens to see which gets priority. In such a way, the system has dynamically allocated resources and self-organized via distributed token networks. In short, blockchain is not just an information technology, but also an institutional technology, in that it enables us to design incentive structures in the form of token economies, and in such a way convert centralized organizations into distributed markets via token economics. This is where things start to get quite complex, as we move into the realm of designing economies and incentive systems for coordinating human activity in a decentralized fashion, something that could potentially enable the coordination of human activity at a much larger scale than has been possible before. The great design innovation of the blockchain is really its capacity to coordinate a network of autonomous nodes towards maintaining a shared infrastructure. And this is done not just through innovations in information technology, but also through the design of incentive systems, which has traditionally been the domain of economics. Through adding a layer of trust and value exchange to the internet, the blockchain merges our newly developed information networks with the institutional structures that sit on top of them. In so doing, it greatly strengthens the capacity of those networks as a new mode for organizing society and economy. By merging economics and technology, it enables us to redesign institutional structures and ultimately reconceptualize how we organize virtually every aspect of society, economy, and even technology infrastructure based on networks of autonomous nodes that are incentivized to collaborate. Of course, it does not do this alone. Such claims can only be realized in combination with other technologies and broader processes of change. As such, the blockchain has to be understood in the context of a broader set of technological transformations taking place with the current evolution of the internet. Most notably, much of what blockchain promises will only be possible given parallel developments in the Internet of Things, datafication and advanced analytics, all of which are combining to form the next generation of Internet, of which the blockchain will be a critical infrastructure. In this video, we're going to talk about the basics of the blockchain as a technology. On its most basic level, the blockchain can be understood as a new kind of database, at least this was its original design. What's different about this database is that it's distributed. Digital databases have been around for a while now, but until recently they've been designed to centralize information on one computer or within one organization. The blockchain, though, uses a distributed network of computers to maintain a shared database. The blockchain is then a set of protocols and encryption methods that enable a network of computers to work together in securely recording data within a shared open database. This database consists of a series of encrypted blocks that contain the data. The blockchain is a continuously growing list of these blocks of data, which are linked and secured using cryptography. This makes it a trusted database, with this trust being maintained by open, secure computer code and encryption instead of any single institution. The database stores information in blocks that are linked together through hash values, with entries to this database being made by computers that all have a copy of the database and all must come to consensus about its state before they can update it. So these are three central concepts that understanding the system's workings, that of blocks and hashing, mining and proof of work, and distributed consensus. We'll go over each of these separately. In terms of its structure, a blockchain may be considered as a series of blocks of data that are securely chained together. New blocks are formed as participants create new data or wish to update existing data. These blocks are encrypted and given a hash value that represents a unique identifier of the data within that block. This hashing works by a standard algorithm being run over the block's data to compress it into a code, which is called the hash, which is unique to that document. No matter how large the file or what information is contained, it is compressed into a 64-character secure hash. This hash value can be recalculated from the underlying file, confirming that the original contents have not changed, but the reverse is not possible. Given just the hash value, you cannot recreate the block's data contained within it, which is encrypted. All blocks of data which are formed after the first block are securely chained to the previous one. This means that the hash value of the next block in the chain is dependent upon the previous one. Thus, once recorded, the data in any given block cannot be altered afterwards without the alteration of all subsequent blocks. As well as this hash pointer linking to the previous block, each block typically contains as well a timestamp so that we know what happened and when it happened. This hashing and linking of blocks makes them inherently resistant to the modification of their data, making them immutable records. You can only write data to the database, and once it's there, it's very hard to change, almost impossible. Thus, data stored on the blockchain is generally considered incorruptible. Blockchain security methods include the use of what we call public key cryptography. A public key, which is a long, random-looking string of numbers, is an address on the blockchain. Value tokens sent across the network are recorded as belonging to that address. A private key is like a password that gives its owner access to their digital assets or the means to otherwise interact with the corresponding data. A public key is associated with the private key so that anyone can make an encrypted transaction to the public key address, but that encrypted message can only be deciphered with the private key that corresponds to that public key. In such a way, effective security only requires keeping the private key private. The public key can be openly distributed without compromising security. For example, on the Bitcoin blockchain, to receive funds from another person, you use a piece of software called a wallet, which creates a public key that you give to someone else for them to send Bitcoins to that address. With your corresponding private key, you can then access that address with those Bitcoins on it. The blockchain is a distributed system. This means there is no centralized organization to maintain and verify the entries on the database. This database is instead maintained by a large number of computers that are incentivized to provide computing resources by earning some form of tokens in exchange. But these computer nodes in the network themselves cannot be trusted individually. Thus, it is required that the system provide a mechanism for creating consensus between scattered or distributed parties that do not need to trust each other, but just need to trust the mechanism by which their consensus has been arrived at. Any computer that is connected to the blockchain network and using a client can perform the task of validating and relaying transactions. Each of these so-called minor computers gets a copy of the blockchain, which gets downloaded automatically upon joining the network. When new entries into the database are made, these changes are automatically broadcast across the network. Mining nodes validate transactions, add them to the block they're building, and then broadcast the state of the complete block to other nodes on the network. In order to randomize the processing of blocks across the nodes and to avoid certain service abuses, blockchains use various timestamping schemas, such as proof of work. Proof of work describes a system that requires a certain amount of resources or effort to complete an activity. Typically, this resource is computing time. As in the case of the Bitcoin blockchain, this is realized on some form of challenge, such that no one actor on the network is able to solve this challenge consistently more than everyone else on the network. Miners compete to add the next block in the chain by racing to solve a very difficult cryptographic puzzle. The first to solve the puzzle wins the lottery. As a reward for his or her efforts, the miner receives a small amount of newly minted bitcoins and a small transaction fee. A consensus algorithm, like Bitcoin's proof of work, functions to ensure that the next block in the blockchain is the one and only version of the truth, and it keeps powerful adversaries from derailing the system. Blockchains are trying to create a secure, trusted, shared database, and they do this through encryption and hashing, proof of work, and network consensus. The hashing and linking of blocks makes it difficult to go back and change a previous block once it's entered, but this alone would not be suffice to ensure that the data is truly tamper-proof. So then the proof of work system intentionally makes it computationally more difficult to alter the database, thus making it extremely difficult to alter all the blocks. On top of this, it places a distributed consensus mechanism, so that even if someone did manage to do this, their record would not match that of others, and thus would not be accepted as a valid record. So to successfully tamper with the blockchain, you would need to alter all the blocks on the chain, redo the proof of work for each block, and take control of more than 50% of the peer-to-peer network. Only then would your altered block become accepted by everyone else. On a blockchain of almost any size, this would be almost impossible to do. Indeed, the Bitcoin blockchain is very good proof of this, given that it now secures hundreds of billions of dollars using this method, without the network having yet been compromised. At the end of the day, what this technology enables is a database that is secure, with automatic trust that is enabled by open source code and encryption. The data is tamper-proof. Once information is put into the database, it cannot be altered afterwards. It is a shared database, as many people across the network have a copy which is continuously being updated, so that all have a single source of truth. Likewise, it is transparent, meaning that everyone can see all of the transactions and alterations made to the database if needed. Data quality and the resilience of the network is maintained by massive database replication across many different nodes on the network. No centralized official copy exists, and no user is trusted more than any other. Having started out life as simply a mechanism to enable Bitcoin, it has become increasingly recognized that this system is secure enough to work as a ledger for the recording and exchange of any value, what we now call a distributed ledger. Over the past years, blockchain has been evolving fast, from the original Bitcoin protocol to the second generation Ethereum platform, to today to where we're in the process of building the third generation of blockchains. In this evolution, we can see how the technology is evolving from its original form as essentially just a database to becoming a fully fledged, globally distributed cloud computer. In this video, we're going to trace the past, present and future of blockchain technology. The first blockchain was conceptualized in 2008 by an anonymous person or group known as Satoshi Nakamoto. The concept and technicalities are described in an accessible white paper termed Bitcoin, a peer-to-peer electronic cash system. These ideas were then first implemented in 2009 as a core component supporting Bitcoin, where it served as the public ledger for all transactions. The invention of the blockchain for Bitcoin made it the first digital currency to solve the double spending problem without the need of a trusted authority or central server. It was only later that we came to really separate the concept of the blockchain from that of its specific implementation as a currency in Bitcoin. We came to see that the underlying technology had a more general application beyond digital currencies in its capacity to function as a distributed ledger, tracking and recording the exchange of any forms of value. The Bitcoin design has been the inspiration for other applications and has played an important role as a relatively large-scale proof of concept. Within just a few years, the second generation of blockchains emerged, designed as a network on which developers could build applications, essentially the beginning of its evolution into a distributed virtual computer. This was made technically possible by the development of the Ethereum platform. Ethereum is an open-source, public, blockchain-based, distributed computer platform featuring smart contract functionality. It provided a decentralized, Turing-complete virtual machine, which can execute computer programs using a global network of nodes. Ethereum was initially described in a white paper by Vitalik Buterin in late 2013 with the goal of building distributed applications. The system went live almost 2 years later and has been very successful, attracting a large and dedicated community of developers, supporters and enterprises. The important contribution of Ethereum as the second generation of blockchains is that it worked to extend the capacity of the technology from primarily being a database supporting Bitcoin to becoming more of a general platform for running decentralized applications and smart contracts, both of which we'll discuss in coming videos. As of 2018, Ethereum is the largest and most popular platform for building distributed applications on. Many different types of applications have been built in it, from social networks to identity systems, to prediction markets, and many types of financial applications. Ethereum has been a major step forward, and with its advent, it has become ever more apparent where we're heading with the technology, which is the development of a global distributed computer, a massive, globally distributed cloud computing platform on which we can run any application at the scale and speed of today's major websites, with the assurance that it has the security, resilience, and trustworthiness of today's blockchains. However, the existing solutions that we have are like extremely inefficient computers. The existing blockchain infrastructure is like a really bad computer that is not able to do much except proof of concepts. Getting to the next level remains still a huge challenge that involves some original and difficult computer science, game theory and mathematical challenges. Scalability remains at the heart of the current stage in the journey that we're on, and this is what the third generation of blockchain technologies are trying to solve. The mining required to support the Bitcoin network currently consumes more energy than many small nations, being equal to that of Denmark and costing over $1.5 billion a year in electricity. A lot of this is being fueled by cheap but dirty coal energy in China, where almost 60% of the mining is currently being done. This high energy consumption is simply not scalable to mass adoption. Ethereum and Bitcoin use a combination of technical tricks and incentives to ensure that they accurately record who owns what without a centralized authority. The problem is, it's difficult to preserve this balance whilst also growing the number of users. Currently, blockchain requires global consensus on the order and outcome of all transfers. In Ethereum, all smart contracts are stored publicly on every node of the blockchain, which has its trade-offs. The downside is that performance issues arise in that every node is calculating all the smart contracts in real time, which results in low speeds. This is clearly a cumbersome task, especially since the total number of transactions is increasing approximately every 10 to 12 seconds with each new block added. The volume of transactions is likewise an existing constraint. With cryptocurrency, speed is measured by TPS, transaction per second. The Bitcoin network theoretical maximum capacity is up to 7 transactions per second, while the Ethereum blockchain, as of 2018, can handle about 15 transactions per second. By comparison, a credit card network is capable of handling more than 20,000 transactions per second. Equally, Facebook may have about 900,000 users on the site in any given minute, meaning that it's handling about 170,000 requests per second. Another issue is that of cost. The fact that it costs some small amount to run the network, so as to pay the miners for maintaining the ledger. What we have is okay for a limited number of large transactions, such as sending money, but making a small transaction, like purchasing a coffee, could not be done by most blockchains. They simply can't, in their existing form, deal with a very large amount of microtransactions, such as would be required to enable high-volume machine-to-machine exchanges. It would prove too expensive to operate these kind of economies that involve many small exchanges, but this is exactly what many people will want to use the blockchain for in the future. In response to these constraints, a third generation of blockchain networks are currently under development. Many different organizations are currently working on building this next generation blockchain infrastructure. Such projects include Definity, Neo, EOS, IOTA, and Ethereum itself. They're each using different approaches to try and overcome existing constraints. Going into the details of how these different networks work is a bit advanced for this course, so we'll just give a brief overview to 2 of them. The Lightning Network is one such project that seeks to extend the capacities of existing blockchains. The main idea is that small and non-significant transactions do not have to be stored on the main blockchain. This is called an off-chain approach, because small transactions happen off of the main blockchain. It works by creating small communities wherein transactions can take place without each of those transactions being registered on the main blockchain. A payment channel is opened between a group of people with the funds being frozen on the main blockchain. Those members can then transact between each other using their private key to validate the transactions. This is a bit like having a tab or an IOU with a shop, where you just mark down what you've exchanged so that you don't have to update the main record in the bank each time you make a purchase. The record stays local between the members involved. The before at some time settling the finances and updating the main bank record. This only requires 2 transactions on the main blockchain, one to open the transaction channel and one to close it. All other transactions happen just within the network without it being registered on the main blockchain. This both reduces the workload on the main blockchain and makes it possible to run very many very small transactions within the sub-network. As of the start of 2018, there is a proof of concept running live on the Bitcoin testnet, but the system will not be fully operational until later in the year, as is the case with most of these projects. IOTA is another example, whereas existing blockchains are sequential chains where blocks are added in a regular, linear, chronological order. The data structure of the IOTA system is able to achieve high transactional throughput by having parallel operations. The data structure is more like a network rather than a linear chain, wherein processing and validation can take place alongside each other. The other big difference is that there are no specialized miners in this network. Every node that uses the network functions as a miner. In the IOTA network, every node making a transaction also actively participates in forming the consensus. That is to say, everyone does the mining. This means that there is no centralization of mining within the network, which is what creates bottlenecks and demands lots of energy. Likewise, with this network, there are no transaction fees for validation. And with IOTA, because it is more user-generated, the more people that use the network, the faster it becomes, which is the opposite of existing systems, and obviously makes it very scalable. There are lots of other possible approaches to overcoming existing constraints. But suffice to say, the blockchain should be understood as an emerging technology, whose existing implementation is like a large-scale proof of concept running on a very inefficient system, but through lots of experimentation and iteration will hopefully in the coming years evolve into this global distributed computer. As Melanie Swan writes in her book, first there was the mainframe PC, personal computer paradigms, and then the internet revolutionized everything. Mobile and social networking were the most recent paradigm. The current emerging paradigm for this decade could be the connected world of computing relying on blockchain cryptography. To understand this better, in the next section, we're going to talk about the blockchain in the context of the broader technological changes that are currently underway as we build the next generation of the internet, what we call the decentralized web or Web 3.0. How we understand the blockchain and where we are with it today is extremely transitory. In this respect, what we're talking about in this course when we talk about the blockchain is really this emerging IT infrastructure of a distributed global cloud computer. The next generation of blockchains will take us a step further on that journey. What we call the blockchain today is really just a very limited and often very inefficient version of this. We still have many very difficult problems to solve before we'll get there. Possibly that end state will look something like the blockchain of today, but possibly it will look very different. People will make big claims about the potential of the blockchain to revolutionize the foundations of social and economic organization. But the blockchain can only have such potential as part of a broader ecosystem of technologies that are emerging as the next generation of the internet, what may be called Web 3.0 or the decentralized web. Today, powerful technological changes are coalescing to take us into a new technology paradigm. These include the rise of advanced analytics coupled with datafication and the Internet of Things. The blockchain will have to work synergistically with these if its true capacities are to be realized. But to understand this next generation web, we need to understand a bit about the history of the Internet. Going back to the early 90s, Web 1.0 was the first generation of the World Wide Web. It was based primarily on the technology of HTTP, which worked to link documents on different computers and make them accessible over the internet. HTML was then used to display these documents so that any connected computer with a browser could access and read a web page. This first iteration of the web was all about information, as it enabled us to exchange information much more efficiently, and hence it got the name Information Superhighway. Even though it was a revolution in information exchange, content creators were few, with the vast majority of users simply acting as consumers of content. It was really very static and lacked interactivity. Whereas in the Web 1.0 era, people were limited to passive viewing of content. With Web 2.0, websites allowed users to interact, collaborate, and become the creators of content. With Web 2, people could not only read from the web, but also write to it, and thus it got the nickname Read-Write Web. By the early 2000s, new server-side scripting technologies such as PHP enabled developers to easily build applications where people could write information to a database, with that information then being dynamically updated every time they refresh the page. Almost all of the websites that dominate the web today are based on this server-side scripting technology. It gave us social networking, blogging, video sharing, eBay, YouTube, Facebook, and all the other large platforms that most people spend most of their internet time using. The idea of Web 3.0 has been around for a while, but it's only very recently, with the development of the blockchain, that it has actually started to become something real. Web 2.0 has evolved to become highly centralized around very large platforms running out of ever larger data centers, creating new issues surrounding security, privacy, control, and concentration of power in the hands of large enterprises. It's only today that these issues are starting to enter into mainstream discourse. Web 3 is set to disrupt this whole technology paradigm, as the critical change that is coming about is that we're decentralizing the web. The blockchain provides the protocols and cryptography for a globally distributed network of computers to collaborate on maintaining a public, secure database. And with a virtual machine like Ethereum, we can run code on this, creating a new set of distributed applications. These new technologies, the blockchain, IPFS, and the distributed web enable us to reconfigure the internet into a distributed global computer, so that we're no longer dependent upon the web platforms and data centers of Web 2.0 to run the internet, but now can build and run applications on this shared global computing infrastructure. As Mike Leopold of the Institute for the Future noted, it starts with the realization that the internet that we know today is only one possible interpretation of the original vision of an open, peer-to-peer network, independent of any centralized technology, commercial entity, or sovereign government. Think of it as a first-curve internet, one that is increasingly vulnerable to abuse and even collapse. To date, we've largely taken the infrastructure of the internet for granted. All of the innovation and action has been focused on the application layer that sits on top of it, on web applications like social networking or e-commerce. With the development of blockchain, and particularly with this third generation, we're starting to innovate on the low-level protocols, asking not if we can build a better web application, but if we can build a better internet. The implications of the decentralized web are indeed radical, and that it enables us to create automated services, disintermediate existing incumbents, and enable people to set up their own secure networks of exchange, empowering them in new ways. The blockchain will be a core part of Web 3.0, but the next generation internet will also see the convergence of the Internet of Things and big data analytics. The ongoing, fundamental process of datafication will be a key aspect to this next generation internet. As we increasingly instrument our worlds, data will flow from all sources about everything. Datafication is the term given to our newly found ability to capture captures data from many aspects of the world and our lives that have never been quantified before. This process results in what we call big data. Vast amounts of unstructured data that can be mined by advanced analytical methods to gain new insight into the world around us. This is important with respect to the blockchain because firstly, it means we'll have a lot of sensitive data that we'll want to store. Secondly, we will be quantifying, accounting for and exchanging all sorts of value that we did not or could not in the past. Thirdly, such a diversity of sources of data, combined with advanced analytics, which can find cross-correlations and patterns within it, can provide a new source to verify the data that is being inputted to the blockchain without depending on a centralized authority for validation. The next generation internet will be much smarter, whereas Web 1 was dumb and Web 2 was dynamic. Web 3 will incorporate various aspects of machine learning and cognitive computing as a service as it becomes infused into almost all applications, making the web truly adaptive, responsive and personalized. Whereas Web 1 and Web 2 were largely about people exchanging information, in Web 3, machines will come online and the internet will become something much more physical, as billions of devices and actuators are connected to all sorts of things, from tractors to watches to factories and drones, enabling them to interact and coordinate machine to machine. The value of the Internet of Things, IoT, will not be in making one device or system smart. It will be in enabling seamless processes across systems. This will require open networks that can communicate and coordinate components on demand across domains, organizations, and systems. The ambition of IoT is not to have our lives populated with thousands of smart things, but instead to change our world from discrete things to service processes. To do this, these technologies will have to communicate securely peer-to-peer, dynamically allocating resources, and this will require some kind of distributed secure infrastructure like the blockchain, and likewise microeconomies. This ties in with the broader process of change which comes about as we move into a services economy called servicization, which is the shift from products and the ownership of things to the access of services on demand. For example, instead of owning a car, you simply have access to a car-sharing service. This economy of temporary usage via services requires the formation of frictionless markets and automated exchanges that the blockchain is well suited to support, as we'll discuss in a future video. These components of the next generation internet, the blockchain, the Internet of Things and advanced analytics, are each of them very powerful technologies that will have a profound effect on society. They will take us much further into this new world of the information age, as power shifts in a radical way from people in hierarchical institutions to automated networks and the algorithms that coordinate them. In the coming decades, more and more of our systems of organization will move to the internet, and it will become vastly more complex than today. In Web 1 and Web 2, we developed the internet from small to large through a client-server architecture that worked to centralize the web around large data centers. But the internet, after datafication and all these IoT devices have come online, will not be large. It will be more like infinite. You can get from small to large by centralizing, but you get from large to infinity through distributing, and that's what the blockchain can do for this next generation internet. Technologies are just tools that enable us to do things. The interesting part of the blockchain is really what it enables in terms of new forms of distributed organization. As one commentator noted, the blockchain is an institutional technology, not an information technology. There's an enormous difference between the two. Institutional revolutions are things that don't happen very often. Blockchain technology enables new forms of networked distributed organizations, something that runs very much contrary to our existing organizational paradigm, and that's what makes it somewhat difficult for us to understand. The organizational model of the industrial age that we inherit today was one of centralization in order to achieve economies of scale through mass production, thus reducing unit cost and